Good day, sir. For today, we'll be presenting our report regarding the vertical farm aquaponic greenhouse. For this project, we formed a group of 4, which consists of Nirtika, Ali Faikal, me, Kendrick Salam, and Vinoshini. Before we go dive in more into this presentation report, I would like to outline what we'll be discussing. So, for this presentation, we'll be discussing about what this project are about, what the problem that we need to solve. Then, we will be talking about the task distribution that we did, as well as the flowchart and coding. And lastly, we'll be discussing about the result. This project are to develop an automated monitoring and control system for vertical aquaponics using an Arduino Uno program in C++. And these systems are simulated in Tinkercad, utilize sensors and actuators to continuously monitor and regulate critical parameters, which for this project, we do the critical parameters specifically such as temperature, soil moisture, water level, and pH level.
Next, we'll be looking at the problem statement of our project. Traditional agriculture is hampered by inefficient resource use and environmental variability, while efficient aquaponics requires intensive, error-prone manual regulation of parameters like temperature and water quality. This necessitates an automated control system to continuously monitor and optimize environmental conditions in both systems, ensuring the peak efficiency and enhancing sustainable food availability for the local communities. Next, we will look at the 4 objectives of our project. The first one is the system development. We have to design, implement, and simulate an automated control system for a vertical farm aquaponic greenhouse using the Arduino Uno system. The second is the monitoring and programming. We have to develop a C++-based control system that will continuously monitor key environmental parameters, such as temperature, humidity, water level. All of this should be done using the appropriate sensors. The third one is the automated control. We have to design and program automated responses for actuators, such as the water pumps, fans, and alarms, to ensure a stable environment condition for both the plants and the aquatic life in our system. And the last one is the safety and feedback. We have to implement safety mechanisms and use a user feedback system via LCD or serial monitors to alert the user when environmental thresholds are exceeded.
Hello, my name is Alif, and in this section, I will be explaining the task distribution for our project. Our first member, Nitika, is in charge of the water level monitoring system. This is to ensure that if the water is below the minimum level, the system will shut down to protect the internal components. Next, I am in charge of the pH level monitoring system. This system displays the pH level and will output an alert if the pH level is higher or lower than the ideal pH level for plant growth. Our third member, Vinoshini, is in charge of the soil moisture control. This system displays the soil moisture level and will activate the water pump for 5 seconds in 10-second intervals if the soil is dry. Lastly, Kendrick is in charge of the temperature control system. If the temperature is higher than the optimal temperature, the fan will activate to reduce the temperature.
Hi, I'm Ritika, and I'm going to explain more about flowcharts and our part of codings. We will begin by looking at the high level of our general flowchart for the initial system setup. The first steps are crucial for ensuring all components are ready before the system starts its work. Starting with the setup, we first handle the LCD setup and assign pins for all of our actuators like the pump and fan, and also sensors like the water level and soil moisture sensors. Next, we set timings and thresholds. This is where we define important values such as the minimum acceptable water level and the dryness threshold for the soil. Once initialization is complete, the system is ready to move into its continuous operational phase marked by the start loop. This is where me and my team members will explain each of our parts for the loops. These are the full code, and we will be discussing part by part for every components. For my part, I will be explaining flowcharts and codings for water level monitoring. Before the system does anything else, it must always check for a critical safety condition, which is low water level. This is an absolute priority because running a pump when the water source is empty can damage the pump or lead to the plant drying out. Let's look at the flowchart, which is directly reflected in our code. As soon as the main loop begins, the system immediately gets the water level and asks, is water level low? If the condition is yes, the system executes an immediate safety shutdown sequence. It triggers the LED and buzzer alarms, and the LCD displays a critical low water message. The corresponding code block shows this. If water level value lower than water level minimum, inside this block we command the pump pin to low, where it will turn off the pump, and use the return to command to immediately stop all other logic until the water is replenished. This is called fail-safe mechanism. If the condition is no, the code proceeds to the else block where the system is cleared to continue to the main operational checks. Now I'm going to explain my part of code line by line. First, low water check. The condition is the code first checks if the current water level value is less than the minimum acceptable threshold. If water level value less than water level mean, action is if the condition is true, the system immediately initiates a shutdown and alarm sequence. Digital right pin pump pin low turns the water pump off as a safety shutdown. Digital right LED pin high turns the warning LED on. LCD is clears the LCD screen. LCD print low water and check water as to display a critical warning message on the LCD. Tone buzzer pin buzzer frequency activates the buzzer delay 500, pauses for half a second. LCD clears the screen again, likely to flash the message. Return is used to stop all further logic in the current function or loop iteration to prevent any component from running while the water level is dangerously low. Second, normal operation. If the condition is false, water level is more or equal to water level mean, the code executes the else block. Digital right pump pin high, the pump is turned on. Digital right LED pin low, the warning LED is turned off. Third, status display. The lines after the if-else block update the LCD with the status message. LCD print, water level value more than or equals water level mean, OK or low. This is a ternary operator that prints OK if the water level is sufficient and low if it is not. This is a final visual confirmation of the water status, which may happen just before the return if the low water condition was met.
As mentioned by Alif, I will be discussing about the flowchart and the code of the temperature control. As you can see from the flowchart, what we want for the code is that when the temperature is high, the buzzer, the LED and the fan will be turned on and the critical message will be printed out, where for here, print temperature is critically high. Meanwhile, if the temperature is not high, then the buzzer, the LED, and the fan will be turned off. For both of the process, we want them to go through the delay process after each of the prompt. This is to make sure that the loop will have time before it going to another loop. Then, for the code, first of all, we need to assign the pin for all of them. For example, here we have the temperature pin, the fan pin, the LED pin, as well as the LCD pin. And we also took the raw temperature and we changed it we convert it into voltage, where here it becomes temperature C or the current temperature. Then we create the code into a loop, which is the Alif loop. If the temperature C, the current temperature, is higher than the high temperature, which is 30 we assign in the first place, then the fan and the LED will be turned on, while the LCD will print out the message high temperature, fan activated. Else, if the temperature is not higher than the temperature high, then the fan and the LED will be turned off. Lastly, after each of these loop, the if statement or the else statement, this code will print out T equal to the current temperature.
So now we'll be taking a look at the soil moisture control. Firstly, with the flowchart, we start, then we get the current millis, and then we see whether the timer is ready or not. If it's not, it comes to an end. If it is, we go to the next one, whether the soil moisture is dry or not. So if the soil moisture is not dry, we go to the end again. But if it is dry, then we would display that the soil is dry and the pump is turned on. Then the pump would be turned on, the LED will be turned on, there'll be a quick buzzer tone. The process will be delayed for 5 seconds, and then the pump will, so that means it's going on for 5 seconds, and then the pump will be turned off, the LED will be turned off, the timer will be reset back to 0, and then the system will come to an end. So now we're going to take a look at the coding and briefly explain each part of it. Some parts are repetitive, so it would repeat again. So we start off with pin mode soil pin input. So this is setting the soil sensor pin as an input. Pin mode pump pin output. It would set the pump control pin as an output. Digital write pump pin low. So this one would make sure that at the start of the thing, the pump is turned off. And then previous pump check millis equals to millis. It would record the current time for the timing control later. So millis in this term would mean that milliseconds, so it's in milliseconds. So then we look at the pump cycle timing check, which we are using the if current millis minus previous pump check millis is more than or equal to the pump cycle interval. So this would allow the system to check whether the soil is fixed every interval, whether to check the soil at every fixed interval. Yeah. And then we have the soil dryness condition. So if soil value is lesser than the soil dry threshold, so if let's say it does not meet the threshold, then you would know that the soil is dry, and then the 5-second irrigation cycle will start from here. So we have a bunch of LCD lines over here. First one is LCD clear, so that would be clearing it to an empty screen. Set cursor to 00, it would be at 0.00, and then the LCD prints soil dry, pump on, moves to 01. It would print begin irrigation. Delay 1000 means it would delay for 1 second because it's 1000 milliseconds. And then LCD clears back again, it's blank. Set cursor 00, it would go back to the 0.00 and write activating pump. And then 01, it would be printing for 5 seconds. And then we have this is the irrigation sequence that's going to happen, the digital write pump in high. So this would mean that the pump is turned on. Tone buzzer pin, buzzer frequency to 500. So this would make a very quick tone from the buzzer. Digital write LED pin high. So this means that the LED light will be turned on. And then we have a delay for 5000 milliseconds, which means for 5 seconds, it would be delayed. So this delay basically means that the pump will be running for 5 whole seconds. And during this time, after that, the LCD will be cleared back. When the set cursor back to 00, it would write that pump is off after the 5 seconds. And then it would write at 01, begin the 10-second wait. So that means the pump would be running for 5 seconds, and then it would wait for 10 seconds.
Thank you, Vinoshini, for the explanation on soil moisture control just now. For my part, I will be explaining the pH level monitoring system. It starts by reading the pH value. For our simulation, the pH level is controlled by using a potentiometer to replicate the pH value. It will then display the pH value of the soil in page 1 of the status screen. If the pH level is lower than the minimum pH level threshold, it will display that the pH level is low on page 2 of the status screen, as well as activate the LED pin and buzzer. And if the pH level is higher than the minimum pH level threshold, it will instead display the level is high, or on page 2 of the status screen, like just now, it will also activate the LED and buzzer. And if the pH level is within the minimum and maximum threshold, it will display a pH level is okay status, and the LED and buzzer will deactivate. Next, here is the full I/O list of components for our system. It contains a red LED to visually alert the user, an LCD display to display the statuses and error messages, a temperature sensor to detect the temperature of the system, a buzzer to alert the user, a soil moisture sensor to check for soil dryness, a DC motor to power the fan and water pump, a H-bridge motor driver to send input and outputs to the DC motor, and a 9-volt battery to supply power to the motors. This is the full diagram of our circuit on Tinkercad. It consists of a LCD screen, an Arduino board, a TMP36 as the temperature sensor, a piezo as the buzzer, a red LED bulb, two DC motors, one is for the fan and the other is for the water pump, a potentiometer to replicate the change in pH levels, two soil moisture sensors, one is used to replicate the change in water levels and the other is the soil moisture sensor to monitor the soil moisture.
I'm going to explain how this water level system works. As we discussed with the flowcharts and codes, when the system first activates or during any loop iteration, its immediate priority is to check if the water level is sufficient in the reservoir. The system constantly compares the current water level reading against a preset minimum threshold. If the water level falls below this threshold, a critical sequence is triggered. First, the system immediately aborts its current operational loop. It then displays a clear low water error message on the LCD screen, as you can see in the diagram here. An LED indicator illuminates and a buzzer activates to provide both visual and audible alerts. Crucially for safety and to prevent damage, the system performs a complete shutdown. This means the water pump and the fan are immediately turned off. This protective measure ensures that pump doesn't run dry, which can cause severe damage and prevents the system from attempting to irrigate without a water source. It's a fundamental safeguard to protect both the hardware and the plant.
As for temperature control as a result, the system is also going to keep track of the temperature of the system. And if the temperature is above the threshold, which is more than 30, then it will turn on the fan and the buzzer in addition to showing an alert.
Over here we have the soil moisture controller. So roughly this is how our system is going to look like. It is going to monitor the soil moisture of the system. And so if the moisture is less than the dry soil threshold, the water pump will be turned on, and in addition to that, it will show an alert, turn on the fan, and also turn on the buzzer.
Thank you, Vinoshini, for the explanation just now. For the pH level monitor, there are two scenarios in case of pH level abnormalities. The ideal pH level range is from 6.5 to 8.5 pH level. So if it is lower or higher than that, the system will display an alert and the buzzer and LED will activate to alert the user as well. Lastly, this is the schematic diagram of our circuit. It was made using our Tinkercad circuit and we had the option to export the circuit as a schematic diagram.
In conclusion, this project has successfully culminated the design and simulation of a self-regulated, automated control system for a vertical farm aquaponic greenhouse using the Arduino Uno and the Tinkercad platform. By writing a C++ code to continuously monitor and regulate parameters such as water level, temperature, and the pH using various sensors such as the TMP36, soil moisture, and etc., and even actuators such as pumps, fans, and buzzers, we all have gained practical real-world experience in embedded systems programming and hardware interfacing. This undertaking, supported by the structured programming course, provided essential hands-on skills in drafting wiring programs, fault finding, and applying structured programming logic to complex engineering scenarios, preparing us for future challenges that will require advanced programming and efficient technological solutions in the green agricultural sector. So we hope that you find this presentation beneficial to you as much as it did for us. That's all from us. Thank you very much.